Now let's talk about the synthesis of amines. The simplest method to use to synthesize an amine is by alkylation. Just as amines can be bases, they can also be nucleophiles, so we might imagine if we treat ammonia with an alkyl halide that we would have an SN2 reaction occur to alkylate that nitrogen atom. This is true, but the process in solution is much more complicated than it is on paper. After we produce this ammonium salt, we still have plenty of ammonia around, which can act as a base, regenerating the alkylamine. If we consider the solution we've created now, we have both ammonia present in solution as well as methylamine. Ammonia is a worse nucleophile and a weaker base. Methylamine is a better nucleophile and a stronger base. This means that methyl iodide will react faster with methylamine than with ammonia. This will produce the dimethylammonium ion, which can then again be deprotonated to generate dimethylamine. You can probably see what's coming. Dimethylamine is a better nucleophile than monomethylamine, so this process will happen again to give me trimethylamine, which is a better nucleophile than all of the previous compounds, so this will react rapidly to produce a quaternary ammonium ion. The way we name or classify this is as a quaternary ammonium ion. This is a nitrogen that has been substituted with 4 different carbon atoms and therefore has a positive charge. This process is called exhaustive alkylation. Here, because we're adding methyls, we might call it exhaustive methylation. We have added as many methyl groups as is possible to our nitrogen atom. This process is not entirely useless, however. It can work if the amine is very, very cheap and readily available, or if you want the quaternary ammonium ion. For instance, if we are trying to alkylate ammonia, we could just use an enormous excess of ammonia, as ammonia is extremely inexpensive. If we do this, that means that the reaction with ammonia is going to be favored by stoichiometry over the slight rate increase that we get by alkylating the compound. The other thing that we can do with this process is make quaternary ammonium salts by exhaustive alkylation. For example, this process can be used to synthesize quaternary ammonium surfactants like cetyl trimethylammonium chloride. This is the structure of cetyl trimethylammonium chloride. Try to make this by alkylation, starting with ammonia as your only source of nitrogen atoms. Take a moment to work on this, then unpause the video and we'll discuss it. The way we would start this process is by taking an alkyl halide and treating it with a large excess of ammonia. This would produce a primary amine, which we could then treat with a large excess of alkyl halide to get different alkyl groups substituted on the nitrogen atom. There are much better routes for amines that need to be substituted at primary carbons or at relatively unhindered carbons, which is synthesis using an azide. If I have an alkyl halide, I can treat this alkyl halide with sodium azide as a source of nitrogen atoms. This will give me an alkyl azide. These azides can then be reduced either with lithium aluminum hydride or by hydrogenation to primary amines. This process works because sodium azide is a very, very good nucleophile and also a relatively weak base. Azide will rapidly undergo SN2 substitution to give alkyl azides. In the presence of a reducing agent like lithium aluminum hydride, this nitrogen will pick up a hydrogen atom, giving this intermediate here, which can then lose nitrogen gas to give an amide ion. This ion is protonated in the presence of water, giving us our primary amine. The biggest limitation to this process is that this must happen by an SN2 reaction, which means that highly hindered primary amines, highly hindered secondary amines, and tertiary amines cannot be prepared by this process. There's another similar route that we can use, which is called the gabriel amine synthesis. The gabriel amine synthesis starts with this compound, which is phthalimide. Phthalimide is relatively acidic and can be deprotonated by potassium hydroxide to give the potassium salt of the phthalimide ion. This ion is relatively nucleophilic and can undergo quick SN2 reactions with alkyl halides to give substituted compounds like this. Now, this imide is not an amine, so in order to liberate the free amine, we have to hydrolyze this derivative. We can either do this using H3O plus and heat, treating it like an amide. This will give us this dicarboxylic acid and an ammonium ion, which can be deprotonated to generate the amine. Another route uses the very nucleophilic dinitrogen compound hydrazine to hydrolyze these and release the amine. The big disadvantage of the gabriel amine synthesis is that it is extremely atom inefficient, as we throw away most of the atoms in our starting material. Let's do a little practice. This compound is saccharin, and it can be used in a process which mirrors the gabriel amine synthesis. If we treat saccharin with sodium bicarbonate, followed by an alkyl halide, followed by H3O+ and heat, we will also get an amine. The questions I have for you about this reaction is, why are we using a weaker base here, and what is the product of this reaction? Pause the video and work through this. Come back when you have a solution. So let's start with the second part of this. What is the product of this reaction? It is this primary amine. As to why we're using a weaker base here, the sulfonate group is going to more greatly stabilize the conjugate base of saccharin, which means that we don't need such a strong base. In fact, the pK of saccharin is about 1.3. It is actually a fairly strong acid. For further practice, propose syntheses of these amines by these methods. So show me how to make amphetamine starting from an alkene, and phenylpropanolamine also starting from an alkene. Use either sodium azide or potassium phthalimide as the source of your nitrogen atom. I'm not going to be discussing the solved syntheses of these compounds. This would be an excellent question to ask me during class. Next, we'll move on to talking about a better synthesis of more highly substituted amines, reductive amination.